Have you ever wondered why a metal spoon in a hot cup of coffee gets screaming hot almost right away, but the ceramic mug itself just feels warm? What's going on there? Well, the answer is this amazing property of matter called specific heat capacity. You can think of it like a hidden rulebook that tells every single substance exactly how much energy it needs to soak up before its temperature starts to rise. And in this explainer, we are going to dive deep into that idea. We're going to start with the absolute basics, the definitions. Then we'll see how a really simple theory makes a shockingly good prediction for solids. After that, we'll check out the weird anomaly of water before we get into the really cool stuff with gases and derive one of the most fundamental equations in all of thermodynamics. So let's get into it.
Okay, first things first, we've got to be really clear about what we're talking about. When we say heating something up, we need to separate the object itself from the stuff it's made of, right? I mean, it obviously takes way more energy to boil a giant pot of water than it does to boil a tiny little cup. But what we're really after is that core property of the water itself. To nail that down, physicists use three different terms. First, there's heat capacity, that's with a big S. This is for a whole object, like one specific chunk of metal. It's the total heat, delta Q, you need to raise its temperature by 1 degree. But of course, that depends on how big it is. So next we have specific heat with a little s. This is where things get really useful, because it's the heat required per unit mass, so per kilogram. This makes it a core property of the material. And finally, there's molar heat, big C. This is kind of similar, but instead of mass, it's standardized per mole, which is just a way for scientists to count atoms. The big takeaway here is this. Specific heat and molar heat tell you about the substance itself. Copper is copper, no matter if you have a tiny wire or a giant statue.
All right, let's kick things off with solids. Now, you'd think that trying to predict the heat capacity for every single solid material in the universe would be just, impossibly complicated. But it turns out a beautifully simple model from classical physics actually gives us a really powerful and surprisingly universal place to start. So to see how we get there, picture a solid as this neat grid of atoms, all connected by tiny little springs. When you add heat, what you're really doing is adding energy that makes these atoms jiggle and vibrate. And they can vibrate in three different directions, up and down, left and right, and forward and back. We call these degrees of freedom. And there's this rule, the law of equipartition of energy, which says that heat energy gets shared out equally among all those degrees of freedom. For a solid, this leads to a pretty amazing prediction. The molar heat capacity for any solid should be about 3 times R, the universal gas constant, which comes out to roughly 24.9 joules per mole per Kelvin.
Now, that is a bold claim, right? To say that we can predict a key property for almost any solid using just one simple number? But does this elegant theory actually work when you test it on real stuff? And the answer is yeah, it works incredibly well. Just look at this data. You've got aluminum, copper, silver, tungsten. They're all packed right up against that predicted limit of 24.9. For most metals at room temperature, the simple model is spot on. But then, you see carbon, way down there at 6.1. And this is what you'd call a brilliant failure. It was a massive clue for scientists, showing that, hey, this classical model is great, but it has limits. It starts to break down. And for things like carbon, you need to pull out the bigger guns of quantum mechanics to get the full story.
Okay, so let's switch gears from solids to maybe the most important liquid there is, water. Water is just special. And its relationship with heat is so fundamental that it was actually used to define the very units of energy we use today.
This whole story basically plays out in 3 acts. First, the original unit of heat, the calorie, was defined entirely by water. It was the amount of heat needed to raise 1 gram of water by 1 degree Celsius. Then, along came James Joule with his incredible experiment, proving that heat isn't some kind of magical invisible fluid, it's just energy. He found the mechanical equivalent of heat, showing that 1 calorie is about 4.186 joules. And that brings us to today, where the standard unit for all energy is the joule, and we know heat is just one form of it.
So what does that number, 4186 joules, actually mean? What does it feel like? Well, that's the specific heat of water. It's the amount of energy you need to heat 1 kilogram of water by just 1 degree Celsius. And to put that into perspective, 4186 joules is enough energy to run a 60-watt light bulb for more than a minute. Water is an incredible sponge for thermal energy.
But here's the catch, the anomaly. That number, 4186, it's really just an average. If you look at this graph, you can see that water-specific heat isn't a flat line at all. It actually changes depending on its temperature, hitting a low point around 35 degrees Celsius. So while the old definition of the calorie was based on a very specific point on this curve, the reality is a little bit messier, which just goes to show that even for something we see every day, the physics can have some surprising twists.
And now we get to gases. And this, my friends, is where things get really interesting. You see, unlike solids and liquids, which barely change their size when they get hot, gases expand a lot. And that creates a fascinating problem.
So here's the core issue. When you heat a solid, all that energy you pump in just goes into increasing its internal energy, delta U, making its atoms wiggle faster. Simple. But when you heat a gas that's free to expand, the energy has to do two jobs at once. Part of it goes into internal energy, making the gas molecules zip around faster, but the other part has to do work on the outside world, pushing against the surroundings as it expands. This means we have to be way more specific and define the exact conditions we're using to heat the gas.
And that whole dilemma leads us directly to one of the most beautiful and important derivations in all of basic thermodynamics. We are about to uncover a deep connection called Mayer's relation that links the specific heat of a gas in two very different scenarios.
So, we're going to build this up piece by piece by looking at two totally separate ways to heat a gas.
Okay, case number 1, heating at constant volume. Imagine our gas is stuck in a cylinder, but the piston on top is bolted down. It can't move. The volume cannot change. Now, the first law of thermodynamics tells us that the heat we add, delta Q, is equal to the change in internal energy, delta U, plus the work done. But since the volume is fixed, delta V is 0, which means the work term just disappears. Poof. So in this case, every single bit of heat we add goes straight into jacking up the internal energy. That means the molar heat capacity here, which we call CV, is just how fast that internal energy changes with temperature.
Now for case 2, constant pressure. This time, the piston can slide up and down freely, keeping the pressure inside the same. So when we add heat, the gas expands and pushes that piston up. Now the heat we add has to be split. Some of it still raises the internal energy, delta U, but now some of it is used to do work, P delta V. It's got to push that piston. So the molar heat capacity now, Cp, has to cover both. It takes more heat to get the same temperature change because you're basically paying an energy tax to do that work of expansion.
So how on earth do we connect these two things? Well, the bridge is the ideal gas law, PV equals RT. With a little bit of calculus, we can see what happens to the volume when we change the temperature while keeping the pressure constant, and what we find is just amazing. That work term from before, P times the change in volume over the change in temperature, it turns out to be exactly equal to the universal gas constant, R. That's it. That's the missing link.
And that brings us to the big aha moment. Let's go back to our equation for Cp. We know it has two parts. The first part, the change in internal energy with temperature, well, we already know what that is. That's just Cv. And the second part, that work term, we just proved it's equal to R. So we just plug those in, and we get this stunningly simple and beautiful result. Cp equals Cv plus R. That's Mayer's relation. The difference between the two heat capacities is nothing more than this fundamental constant of the universe. And this gives us the perfect mental picture for why this works. Think about it like a balance scale. When you heat a gas at constant volume, Cv, the energy you put in only has one job to do, raise the temperature. But when you heat a gas at constant pressure, Cp, that energy has to fight a two-front war. It has to raise the temperature and it has to fight the outside pressure to expand. And that extra energy it needs to win that second battle, that's exactly R.
So let's just take a step back and pull all of this together. We've gone on a journey from tiny vibrating atoms all the way to expanding engine pistons.
We've really seen 3 big ideas. For solids, we saw the law of equipartition gives us this amazing prediction that the molar heat capacity is around 3R. For water, we saw how it literally defined our units of energy, but also that its own specific heat isn't even constant. And finally, for gases, we derived Mayer's relation, Cp minus Cv equals R, which perfectly explains how the work of expansion makes all the difference.
And that really is what this is all about. Specific heat capacity isn't just some random number you look up in a chart. It's a truly profound idea that connects the invisible, microscopic world of jiggling atoms with the big, macroscopic world that we can actually see and measure, the world of thermometers and steam engines. It's a perfect example of how these fundamental laws of physics let us understand and predict how the world works, all from one simple question: how much energy does it take to get a little bit warmer?